Very good evening, students. Welcome back to the JEE Advanced discussion. Okay, we are back here with a new chapter. Okay, and one of the very important topic in the JEE Advanced. Right. Hope all of you are doing fine. Right, and hope all of your preparation is going very well. Okay, right. So let us discuss some of the few concepts involved and with the help of the numericals. Okay, mainly in the modern physics, you are having dual nature of matter, right? That regarding the photons and how they will exert the forces on the surfaces, right? And then you are also having in the photoelectric effect, okay, problems including the photoelectric effect, and after that you are also having the Bohr's hydrogen model problems, okay, and also the other chapter, that is the nuclei, right? In the nuclear physics also we are having two models. One is regarding the radioactivity, the other one is regarding the binding energy concepts. Okay, so we'll discuss the problems which are involving in all these sub concepts and also the previously JEE advanced problems, right? Okay, so we'll start discussion. Okay, some little few concepts before exactly starting the numericals. So every photon, whatever you take, it is having an energy of hc by lambda, energy of each photon, right? And it is having a momentum of h by lambda. Any photon will have a momentum of h by lambda. And whenever there is a source which is emitting the radiation, which is having some power P, source is having the power P, and always the question is how many photons that it is going to emit per unit time. Suppose if this is emitting with a power P, that means how much energy it is emitting per second means P. So number of photons will be equal to power by energy of each photon, which is equal to hc by lambda. So that you will be getting number of photons emitted by this particular source, right? Okay. Next, further, one more discussion. This energy of photon, the momentum of the photon, right? And one more discussion. Suppose if they are giving the energy of the photon, which is hc by lambda, and momentum of the photon is h by lambda, it means that you will have a momentum of the photon can also be written as energy of the photon divided by c, right? If you divide this by c, you will get h by lambda, which is called as the momentum of the photon. So these are all little useful things, okay, in solving the problems, okay, right? And one more thing, whenever any particle striking a surface at some angle and reflecting with the same angle, suppose this theta, particle is having some momentum p and reflecting with the same momentum p in a different direction, right? Then what is the change in momentum? Definitely when the particle hitting this and rebounding like this with the same angle, so what is the change in momentum of this particle? How much you will be having the change in momentum of this particular particle? Because the momentum will be changing only in this direction. If you take for this particle only in the common normal direction, right? It is something like an oblique collision, right? So here you will have p cos theta, and this is a p sin. One is p cos theta and the other one is p sin theta. In this direction, momentum is not changed. Only perpendicular to this plate, momentum is changed. So that is why change in momentum you will be getting 2p cos theta. Okay. I hope that is clear to all the students. Right. So you are just taking, this is one component, this is another component. Here it will be like this and like this. So these components are not changing, these components are changing in the opposite direction. So that is why 2p cos theta. All right. And suppose one more basic concept will be like whenever continuously particles are coming and hitting the surface, continuously some particles are coming and hitting the surface, right? Then if you take suppose one electron is there, which is having some momentum p, and this is the surface, okay, like that so many electrons are hitting, continuously. Okay. Now, when it is hitting, they can reflect also, they can absorb also. Right. This surface can absorb the electrons or they can reflect the electrons. Same thing goes for the photons. Photons are hitting, whenever photons are hitting the surface, it is something called as the force what it will exert on this particular surface, whatever the force that it will exert on the surface, that is force by area, we are calling it as radiation pressure. So that is one more concept. And here when continuously electrons are coming and hitting the surface, so we will take a change in momentum of each electron, into number of electrons hitting the surface per second will give you force, right, where n is nothing but number of electrons hitting per, that is nothing but the, so change in momentum of each electron into number of electrons hitting per second will give you the exactly force exerted by the electrons on this particular surface. Means total change in momentum you will get by time. So total change in momentum by time is nothing but the force only. So these are all little useful things, okay, in solving of the different numericals, right? Okay, right. So with these ideas, we'll proceed further into the solving of the problems. So here is the first question. A perfectly reflecting solid sphere of radius small r is kept in the path of a parallel beam of light of large aperture. Okay. Parallel beam of light is having large aperture. If the beam carries an intensity I, find the force exerted by the beam on the sphere. So first thing, reflecting. Okay. This problem, suppose if it were absorbing, for example, okay, this problem, suppose if it were absorbing, so the parallel beam of light, what you project. So this is a parallel beam of light, right, whose intensity is I. And all this parallel beam of light, whenever it is falling on this surface, you will take just the, and perfectly absorbing. If at all, if it is perfectly absorbing, you will take the projected area of that, correct? And projected area is pi r square, right? If it is perfectly absorbing. Then later I'll also solve for reflecting. So perfectly absorbing, then you will take the projected area pi r square into I by C. This is what you will get the force. Means radiation pressure, that is I by C into that projected area pi r square. This is what you will be getting when it is perfectly absorbing. Okay. Now what is that you are going to get when it is perfectly reflecting? This is what we'll try to find. Okay. Carrying an intensity I. So let us also try to check what exactly is the intensity formula. I mean, intensity is nothing but the energy falling on that per unit time per unit area, right? So energy falling on that per unit time per unit area. So whatever the energy you are getting, right? Or simply energy per unit time is nothing but power by unit area, right? So these are all the useful things. Total energy, how much it is falling per unit time per unit area, that is what the intensity. Now let us start solving the numerical, right? Okay. So I'll draw the figure. So it will not be sufficient over here. Okay, there is a reflecting solid sphere. Now it is reflecting, it is not absorbing. Okay, it is reflecting, right? And then how much force that it is going to exert, what is the force exerted by the beam on the sphere when it is completely reflecting, perfectly reflecting. So for that, what exactly you have to take. Okay. So I will consider here like this. This radius of the sphere is smaller, they have given, right? Radius of the sphere is smaller, right? So smaller radius is given, intensity is given, and reflecting is given. You have to find the force exerted. Hope the question is very much clear to all the students. So actually what happens is, its beam is coming here. Suppose if it is coming here, it will reflect like this. Beam is coming here, it is reflect like this. Correct or not? That means all the photons coming and hitting and they are getting reflected. So each photon is changing the momentum, no? So every photon is changing the momentum. So whenever the photons are changing the momentum, they will exert some force, because they will receive some force from the sphere. Same force they will also exert on the sphere. In that way, we have to calculate, right? So many photons are there. Of course, the photons which are coming exactly normally, then it may reflect like this. That's okay. But remaining all, they'll reflect like this, no, at some angles, right? So there are changes in the photons momentum. So whenever there is a change in photon momentum, okay, definitely some force will be exerted by the sphere on the photon. So same force photons also will exert on the sphere. That force only they are asking, right? Now let us start solving. Here first I will consider one small strip on this. I will draw one small strip on this. It will look like this throughout, small strip, right? But the other side also. Okay. Now if you put it in another way, this one I can also take it like this. Small ring type you will get. Okay, if you cut it here, just a small ring you are getting. This is actually center. Okay, this is your smaller radius, correct? And you will take some theta here. You take some theta, right? Take this normal. Is it not normal to this? And similarly here also you take one normal, and you take one line like this. So assuming this as, so this is small r. So obviously this value will become r dash, right? Which is nothing but r dash is nothing but r sin theta. Yeah, right. Now we are also interested to find what is the area of this strip. Okay. Completely, what is the area of this strip we are taking. Here, the strip, it is subtending an angle, small angle called as d theta at the center, right? So because the strip is actually like this. This is the center. So it will subtend because it is having some thickness. It will subtend an angle d theta exactly at the center. Hope it is clear. And this is your theta. Right. Next, we are interested to find the area of this strip first, because all this will help us in solving the problem. Because problem solving, what I am doing is, I'll take the momentums hitting and rebounding, right? So change in momentum and all. So first, let us also try to calculate what is the area of this strip. So area of this strip, if I call it as some dA, how much you will get? First of all, total circumference of this, okay, 2 pi r dash, circumference 2 pi r dash into thickness, correct? So total 2 pi circumference, that is 2 pi r dash into thickness. Thickness, how much you can get? Is it not this thickness? Can I write it as small r into d theta? Okay, take it. So once again, so this thickness you are talking about, this is small r, this radius is small r, into d theta will become the thickness into total circumference, which is 2 pi r prime. Thickness gives you the area of this strip, whatever you are trying to select. Okay, what is the use of that area of the strip? First, we will consider photons are hitting this strip. In that way, I will try to consider and I will try to solve it, right? So here I can write it as 2 pi into what is r dash? R sin theta into r. So 2 pi r square sin theta d theta. Yeah. Okay. That area of the strip we have calculated. Now, assuming, let us say one photon is hitting like this and it will rebound like this, perfectly reflecting. So definitely this angle and this angle will be equal. And you know this angle is theta, so this angle also will be theta. So photon is coming like this, hitting and going like this, right? So let us say initially the photon is having some momentum p. Initially the photon is having some momentum p. After rebounding, also it will have momentum p, but in a different direction. So what will be the change in momentum of a photon, one photon? So just assume that it is hitting here like this. It's a completely three-dimensional. So wherever it hits, accordingly it will go. So total that ring, whatever you are selecting, okay. Here also one photon is coming like this, hitting and rebounding. Agree? This is also theta. So this is also theta. So change in momentum of each photon, one photon. So what is the change? As I told you, the theta and theta. So it will be, when it is having a momentum as p, going with p like this. So what will be the change? 2p cos theta. Already I told you, where p is the momentum of the particle, right? Okay, so that is a change in momentum of the photon, and it will be in this direction. Change, because this vector minus this vector, if you do, you will get in this direction, right? Okay, so in that direction, change in momentum is sphere will exert the force in this direction. So photon will exert the force in the opposite direction. Is that clear? Right. Okay, so after taking changes like this, and one more important thing I will add here, let capital N is equal to number of photons striking the sphere per unit time per unit area. This is very important. How many number of photons are striking the sphere per unit time per unit area we are taking. So that is called as N. Okay, number of photons striking the sphere per unit time per unit area. Now this is the change in momentum of one photon, right? But now I want the force exerted by all the photons. Okay, force exerted by all the photons. And here one more thing also you have to take is, actually the area is not exactly whatever dA you are taking, it is not exactly facing the photons. The whatever the dA you are taking, this is not exactly normal to these photons, right? It is slant like this. Slant was there. So what is the exposed area towards hitting of the photons? Photons are hitting that area. That area is not normal to that photons. It is little bit of slant is there, no? So for that also I have to take the thing, that is, this is the area what you are selecting, and photons were coming like this, isn't it? So this is the area which I have written dA. Whatever dA I have written, this was the area, but photons were coming like this. So what I do is, I will take the area, this one, which is normal to the incident photons. Okay, so since this was theta, definitely this will become theta. So this will become some dA dash, which is equal to dA cos theta. So the dA cos theta is the area, I mean something like a projected area which is normal to the incident photons, right? That also I have to consider. Whenever you write that area, okay, you have to consider that one also, right? Because some photons are hitting here, some photons are hitting here, some photons are hitting here. So better you take the effective area only, right? So getting back here, so change in momentum of one photon is 2p cos theta. Now force exerted, so we are talking about the force exerted. So force exerted will be equal to change in momentum of one photon into total number of photons. Okay, we are talking about force exerted only on the strip. Force exerted by these photons on this strip will be equal to change in momentum of one photon into how many number of photons which are striking the strip. So the total number of photons which are striking that strip will be, already you know, the per second. Total number of photons which are striking that strip per second means already number of photons striking the sphere per unit time per unit area is n. So total number means, so you have to multiply with n into area of the strip. What is the area of the strip? dA. See, per unit area is n. Okay. Then total dA area, how many photons are striking means n into dA. So these are the total number of photons which are striking that area dA per second into change in momentum of each photon. Gives you force exerted on this particular strip. And one more thing, you have to take dA or dA dash means definitely you have to take dA dash. So again I am making this thing instead of dA because that total area which is projected normal to this is dA dash. So you have to put dA dash. Right. So that comes out to be 2p cos theta change in momentum of one photon into number of photons striking the sphere per unit area per unit time into how much area which is exposed, that is dA cos theta. dA cos theta. This is a force. We are talking about the force exerted by all these photons on this strip. And of course, they will exert in which direction they will exert the force, like this they will exert. They are going to exert the force like this, not like this. Right or not? Okay. So 2p cos theta into n into dA cos theta. So what is dA? Substitute for dA. 2 pi r square into sin theta d theta, all that. Okay. So this one further 2p cos theta into n dA cos theta. So force. Okay. So that is only force acting on that strip. So we'll write dF. Okay. So what was that? 2p cos theta into n dA cos theta. dA dash, which is dA cos theta, and substitute for dA also. 2p cos theta into n. So what is dA? dA is equal to 2 pi r square sin theta d theta. D theta and cos theta. Right? Okay, so that is the dF. We can nicely write this as, I think, so 4 pi r square, 4 pi r square, right? P n, right? So sin theta is there, also cos square theta is there, so d theta. This is the force what they will exert, okay, on that strip only. And one more thing, which direction they are exerting this force? Are they not exerting the force in this direction actually? Because change in momentum of the photon is in this direction. So force exerted by the sphere on the photon will be in this direction. So photons will exert the force in this direction. Similarly, here also it will be in this direction. So throughout that strip, like this, it will exert, right or not? So for that you have to take the resultant, because some components will get cancelled, right or not? So which components are getting cancelled? These vertical components will get anyway cancelled. So definitely horizontal components will be there. So what are those horizontal components? dF into again cos theta only, right or not? So here, suppose if this is a force and here this is a force, okay. So these vertical components, horizontal will be remaining and vertical will get cancelled, right? These will get cancelled, so they will remain horizontal. So for all those, horizontal only will remain there. So that is why the total force, it is not dF, rather it is equal to dF dash is equal to dF again cos theta only. So you will be getting 4 pi r square p n, okay, sin theta into cos square into cos cube theta to d theta. So overall how much all these photons are exerting the force on that particular strip, okay, is this one, right? Then, but you know what? These are the number of photons striking the surface per unit time per unit area, and this is the momentum of each photon. I already told you momentum of each photon is equal to energy of the photon by c. Momentum of each photon can be written as energy of each photon by c. So df prime is equal to 4 pi r square. P is what? E by c to n to sine theta into cos cube theta into d theta. Okay, next, energy of each photon into number of photons striking per unit time per unit area. Okay, number of photons striking per unit time per unit area into energy of each photon gives you total energy which is striking per unit area, total energy which is falling per unit area per unit time, and total energy which is falling per unit area per unit time is nothing but intensity. Okay. So you are using n is always number of photons striking per unit time per unit area into energy of each photon gives you total energy falling per unit time per unit area, which is nothing but intensity. So simply I can write this n is nothing but intensity. So df prime is equal to 4 pi r square. N is intensity by c into sin theta into cos cube theta into d theta. This is the only force which is exerting only on the that strip, ring like strip what you have taken, right? So but such type of strips, because they are asking force exerted on the total sphere, we have so far only calculated the force exerted only on this ring like strip, right? Only on this strip was calculated, which is making an angle theta, right, and subtending an angle d theta. Like such type of strips I can take it here also. If I just cut it like this, okay, so I can take such strips from 0 to theta varying from 0 to 90, because force will not exert on this anyway, right? Photons are falling like this. So simply integrate from theta is equal to 0, you will get this strip, to last strip theta is 90. Okay, so integrate this from 0 to 90, total force F prime, this is the final answer, total force. Okay, so 4 pi r square I by c. So integration of sin theta into cos cube theta into d theta from 0 to pi by 2. And we know how to integrate this sin theta into cos cube theta into d theta. So just by substitution methods, you can employ a substitution methods there. So that substitution methods, I will take this the next page. So 4 pi r square I by c. So total force, right, 4 pi r square I by c, integral of sin theta cos cube theta d theta 0 to by 2, right? So let cos theta is equal to some x, okay, then you will be getting minus sin theta into d theta equal to dx. So that integration will be simply sin theta is dx and cos theta is x, right? So minus you will get, okay, x cube into dx, take it, because sin theta d theta is what? Minus dx, and cos theta, yes, that's it. So which is nothing but minus of x power 4 by 4, x power 4 by 4, x is what? This one. So cos power 4 theta by 4, substitute the limit 0 to pi by 2. Now first you substitute in pi by 2, so 0 minus, then you substitute 0 minus 1 by 4, so equal to 1 by 4. So that integration will give you 1 by 4. So finally your force will be nothing but 4 pi r square I by c into all this integration will give you 1 by 4. So your force will become simply pi r square I by c. Okay. It's becoming pi r square I by c. All right. So this is exactly in tune with the force exerted by the electromagnetic radiation when it is perfectly absorbing. Okay, but of course here it was reflecting in a different direction, but maybe you might have got, but that doesn't mean that when it is reflecting and absorbing for all the cases, right? So, and this is for perfectly reflecting, okay, what you are getting pi r square I by c, and even when the sphere is there, as I told you initially, it is falling and the perfectly absorbing also, you are getting the same formula. At times simply you will use projected area, isn't it? So that projected area concept you will use for perfectly absorbing, right? Not for reflecting, because if it is reflecting in a separate direction. But luckily you are getting the same answer. That doesn't mean that it will apply for all, right? All this you are doing. Okay, so hope this is clear. So this question mainly intention is very simple, that change in momentum of the photons and how the force it is exerting, but each and every minute way how you are able to take and what is the meaning of the intensity mainly, right? So all this taken into account, so that has been the problem. Okay, hope you have able to make this question. All right, next one. Let us get back to the next question. Now, a silver sphere of radius 1 centimeter and work function 4.7 electron volts is suspended from an insulating thread in free space. It is under continuous illumination of 200 nanometer wavelength of light. 200 nanometer wavelength of light is continuous illumination. As photoelectrons are emitted, sphere gets charged and acquires a potential. The maximum number of photoelectrons emitted from the sphere is how much? Right? See, to suddenly look at this, what was happening? Sphere suspended, insulating thread. So it is continuous illumination of some light. So light is falling, right? Whenever light is falling on this, electromagnetic radiation is falling on that, electrons are ejected. And as and when the electrons are ejected out, so it is a silver sphere, it is a very good conductor. Electrons are ejected out, it is acquiring the positive charge. So when it is acquiring some positive charge and electrons are ejected out, after some time what happens? So some number of electrons are already came out, so it has acquired some positive charge. Because of that positive charge, next electron when it is trying to eject, okay, it will, by the time it ejects like this with some kinetic energy, by the time it goes here and again it comes back. That much potential it is high. Earlier they were going to infinity, right? Now it is acquiring more and more positive charge. So then that it becomes more and more difficult for the further electrons to eject out from that particular silver sphere. Okay, so it is something like first, with what kinetic energy they will eject out. So for that, what I will do immediately, whenever the work function is given and illumination of light, the electromagnetic radiation 200 nanometers wavelength of light is given, immediately I will find out first energy of each photon, right? So that is 200 nanometers. So I'll take so how do you convert that into electron volts? How do you convert this wavelength? So you are using hc by lambda, but direct formula is also there. Okay, so 1240 by 200. This is 1240 electron volt nanometer by 200 nanometers. This is a direct formula which will apply, correct? When it is coming to angstroms, then you will use 12,400 by lambda in angstroms, but in nanometers you will use this, okay? And this value you are going to get it as how much? So 6.2 electron volts energy of each photon. Once you get energy of each photon is 6.2 electron volts, and what is the work function? 4.7 electron volts. So write the photoelectric equation, work function, okay, energy of each photon is equal to work function plus K max, right? So this 6.2, work function is 4.7 plus K max. What will be K max? 6.2 minus 4.7, 1.5 electron volts. So this is the kinetic energy what the electron will get, right? So with this kinetic energy, will it escape to infinity? Okay, initially they were escaping to infinity because not much positive charge was there. After some time, they may not escape to infinity, because it will acquire some positive charge. Because of it, it will have some potential, and that because of that potential, these electrons are unable to escape. Even though they will eject with some kinetic energy, they will go like this and then again come back. They cannot go up to infinity. So that means this potential, whatever it has acquired, okay, that will trying to stop this electrons, definitely. So what is the step that you have to make here? Let us say it has acquired a positive charge of Q, right? So once it has acquired a positive charge of Q, what will be its potential? Is it not KQ by R potential? That is nothing but KQ by R electrostatics. K is 1 by 4 pi epsilon naught, which is 9 in 10 power 9. Okay, Q is the charge, what it has acquired, positive charge by radius of that sphere, right? Okay, so this is a potential, and that potential, whatever it has acquired, suppose if you take electron, okay, electron will have a kinetic energy of this, right? And when the electron is just ejected from here, right, and it should at the most go to infinity. Okay, it is unable to go to infinity first of all, right? So what you will do? So is it not this potential, is it not acting like a stopping potential for these electrons, right or not? So this potential, whatever is acquiring, it is trying to stop these electrons. Just like in the photoelectric effect also, we were taking that K max is equal to E into V naught. K max is written as E into V naught, where V naught is called as the stopping potential. Here the same thing, stopping potential, there is no anode, of course, because it's at infinity. So this potential only can be treated like a stopping potential, right? So for kinetic energy K max 1.5 electron volts, this potential, exactly what is the related potential for this? Okay, when see it is electron volt only, no, and your which are escaping, electrons only escaping, coming out. So why, when the electrons will get this much kinetic energy, when they are accelerated under a potential difference of 1.5 volts, correct or not? Whenever any electron is accelerated under a potential difference of 1.5 volts, they will acquire a kinetic energy of 1.5 electron volts. So that is why this stopping potential is simply 1.5 volt. This is a stopping potential which is acting like a stopping potential is 1.5 volts, because it will stop the 1.5 electron volts kinetic energy of the electron. To stop a, see, simple, I'll put you like this. To stop an electron which is having a kinetic energy of 1.5 electron volts, you need a potential difference of 1.5 volts or not. Okay. Or same thing, to accelerate an electron from 0 kinetic energy to 1.5 electron volts kinetic energy, then also you require potential of 1.5 volts. Only thing is the which is positive, negative, that will vary. Okay, right? Whether to accelerate or decelerate, you want the potential difference, correct or not, of 1.5 volts. So now you want to decelerate the kinetic energy from 1.5 electron volts to 0. So you need some potential, stopping potential of 1.5 volts, and that potential is nothing but potential of the sphere, 1.5 volts. Here you are taking 1.5 volts, right? Okay. Now calculate what is the charge. Why the sphere is having that potential? Because of a charge. Okay. How much is that charge? So just check it. K is 9 in 10 power 9. Okay. To Q by R 1 centimeter. So 10 power minus 2 is equal to 1.5. Just calculate the value of Q first. 1. The value of Q will be 1.5 into 10 power minus plus to minus 2 by 9 into 10 power. This is the total charge what it will acquire, coulombs. But I want how many electrons? So they are asking maximum number of photoelectrons emitted. Because every electron when it is emitting, it will acquire a charge of 1.6 into 10 power minus 19 coulombs, positive charge. It will acquire if it is emitting 1 electron. Like that, if it has to acquire total of this much charge, how many electrons it will acquire, emit? So this is nothing but total number n. So charge of each electron 1.6 into 10 power minus 19 charge of each electron. is equal to 1.5 10 power minus 2 by 9 into 10 raised to, what is the value of n then? 1.5 into 10 raised to minus 2 by 1.6 into 9 into 10 raised to 9 into 10 power. Do this calculation. So it will be roughly 9 and minus 19, you get 10 power minus 10. So that will go up 10 power plus 10, right? 10 power plus 10 and minus 2, 10 power 8. Okay, 10 power 8. But here you will be getting something like 1.1 into 9 almost. Okay, so 1 point something into 9. Okay. So 9 point something you will get. 9 point something, 9.9 or 9.1, whatever. Right? So that is close to like 0 point something, 0.1 or something into 10 power. Okay. So how much? 9 is there already here, more than 1. So 1 point something, 10 point something. So you'll get something like 10 power 7. Like all these calculations. And clearly they have given that A into 10 power Z. And A is a number which is running from 1 to 10. So 0.1 into 10 power 8 you will get. So 1 point something into 10 power 7 you will get. 1 point something into 10 power 7. So answer is, because A is a number which is from 1 to 10, 1 point something 10 power 7. So answer is the answer. Right? Okay. So the calculation part, properly make it. So this is a JEE Advanced 2011, what you got the question. Right? Okay. So we'll proceed to the next question. Again, in a photoelectric experiment, a parallel beam of monochromatic light with a power of 200 watts. Power of the light is 200 watts is incident on a perfectly absorbing cathode of work function 6.25 electron volts. Okay, the frequency of light is just above the threshold frequency. Just above the threshold frequency. So that means this is a cathode and perfectly absorbing. So this power is falling on this, and whatever the energy of each photon is there, it is just able to remove the electron. That's it. It's just slightly above the work function. So that means definitely the electrons will be ejected out with zero kinetic energies, negligible kinetic energy. That's what they have given. So frequency of light is just above the threshold frequency, so that the photoelectrons are emitted with a negligible kinetic energy. So they don't have any kinetic energy when they eject out from the cathode. Assume that the photoelectron emission efficiency is 100%. What do you mean by photoelectron emission is 100% means how many photons are incident on this plate per second, same number of photons will be ejected out per second. That is what photoelectron emission efficiency, right? So the number of photons incident per second will be equal to same number of electrons will be coming out. So that means each photon is able to remove one electron. And the potential difference of 500 volts is applied between the cathode and the anode. Okay, so you are also putting one anode here, anode plate here, anode plate you are putting. So these and you are creating some potential difference of 500 volts. So whenever you create a potential difference of 500 volts, so these electrons will get accelerated and they will acquire some very good kinetic energies. In fact, how much kinetic energy they are acquiring means, because they are accelerated under a potential difference of 500 volts, they will acquire a kinetic energy of 500 electron volts, because electrons. So they will acquire a very good kinetic energy of 500 electron volts. With that, they will hit this anode. Okay. Okay. So they are hitting that anode. All these emitted electrons are incident normally on the anode and they are perfectly absorbed. Okay. That means every electron momentum has become zero after hitting. Right? So that means there is a change in momentum of so many electrons. So when there is a change in momentum of these electrons, electrons are receiving some force by the anode. So whatever the force that is anode is exerting on the electrons, electrons also will exert the same force on the anode. And that force they are asking us to calculate. The anode experience a force, so and so, due to the impact of the electrons. And we have to calculate that particular force. Okay, hope the question is clear to all. Right, it's very simple only. So just we know that every electron will acquire a kinetic energy of 500 electron volts. So you know the momentum, right? Now again I am using that fact that force exerted is equal to change in momentum of one electron into number of electrons hitting per second. And how many number of electrons are hitting per second means how many number of electrons ejected out per second. And how many number of electrons ejected out per second is nothing but how many photons are incident per second. Why? Because photoelectric efficiency is 100%. Okay, so first we have to calculate how many photons are incident on this metal plate. And how do you calculate that? How many photons are incident on the metal plate? Number of photons incident on the metal plate will be given by number of photons incident per second is given by, already I told you, power by energy of each photon, right or not? Power by energy of each photon. And what is the energy of each photon? Again, energy of each photon. Energy of each photon is such that electron is just slightly, energy of each photon is such a way that it is slightly greater than the work function. Because clearly they have given frequency is slightly above the threshold frequency. So that means energy of each photon is slightly greater than the work function. So you can take almost it is equal to the work function. The work function is 6.25. So that means energy of each photon is also 6.25 electron volts, right? So but the power they have given in watts. All right. So how do you calculate? So power is 200 watts. Energy of each photon is 6.25 electron volts. 6.25 electron volts. Please try to convert it into joules. So into 1.6 into 10 power minus 90. So 1 electron volt is equal to 10 power 1.6 10 power minus 19 joules. 6.25 electron volts is equal to 6.25 into 1.6 into 10 power minus 19 joules. So these are the number of photons which are incident on this per second. Again per second only. Why? Because power is energy joule per second. No, this one as we know it is joule per second and this is in joules. So joule cancels per second. So that's what number of photons incident per second you will get. So how much is this one? First let us calculate these things. Per second. So how much? 206.25. All these calculations. Try to make it. So think or keep it like that. 200 by 6.25 to 1.6 into 10 power. Some very good number because 10 power 19 is going up. Very good, huge number. Right. Okay. So these many photons are incident on this. So same number of electrons also. How many number of electrons are ejected out per second means same. How many number of electrons are hitting the anode also same per second. Okay. Now, and each electron energy is how much? 500 electron volts. So when each electron energy is 500 electron volts, this is a metallic surface, electron is there and it's having a kinetic energy of 500 electron volts because they are accelerated under a potential difference of 500 volts. So they will acquire a kinetic energy of 500 electron volts. So they have, let us say, K is a kinetic energy. So once the kinetic energy of the electron is there, you know how to find the momentum of the electron because momentum is equal to under root of 2 km. The relation between momentum and momentum of a particle and kinetic energy of a particle is momentum is equal to under root of 2 km, right? So that is a momentum. Change in momentum is also this one only because final momentum is 0. Why? Because it is perfectly absorbed. So this will be the change in momentum also. So change in momentum of one electron is this one. Of course, change in momentum is also equal to root of 2 km. This is a change in momentum of one electron into number of electrons striking per unit time will give you the force exerted. Simple. Okay. So that I will write. I want to calculate the force change in momentum of each electron to number of electrons striking per unit time. So total change in momentum of all electrons per time gives you force. That's it. So change in momentum means root of 2 km to n. This is your force. Rest is only calculations. So 2 into kinetic energy, 500 electron volts. So 500 electron volts. So you can write 500 into 1.6 into 10 power minus 19. Yes or no? Into mass of each electron is also there. So 9 into 10 power minus 31. That is a momentum into number of electrons, n value. This will become 10 power minus 50, right? Minus 19, minus 31, minus 50. Come out as 10 power minus 25 outside. Okay. Next, here 10 square, so it will come out as 10 outside. Next, 5 into 2, 10, 10 into 1.6, 16. 16 will come out as 4, and 9 will come out as 3. Okay. 20, 10 power minus 25 means 12 to 10 power minus 24. That is the value of this under root to n. Now you substitute n also. N is what? 200 by all this. Okay. Substitute that 200 by 6.25 into 1.6 10 power minus 19. 200 by 0.25 into 1.6 over. Check it. So this will be the only calculation, right? Approximately how much? 4 is there, 25 is there. All calculations, please try to make it. And 10 raised to 19, 1 plus 24, 10 raised to minus 24, and here it will come as 21. 3. Remaining all 12 into 2 by 6.25 into 12 to 6.25, 1.6, yeah. So minus 26. So 12 into 24 and 6.25 into 16. Okay, 1.6. How much? I think this will become 6.25 into 1.6 will become 10. So you will get 24 into 10 power minus 3 and minus 4 newtons. So that is the total force experience. Okay. So 24 into 10 power minus 4, and they have given n into 10 power minus 4. So the value of n is 24. Hope it is clear. Next, we'll proceed to the next question. Take this question. A photoelectric material having a work function of phi naught is illuminated with a light of wavelength lambda, and lambda is less than the hc by phi naught. The work function is given and is illuminated with a light of wavelength so and so. The fastest photoelectron has a de Broglie wavelength. See, they did not give the kinetic energy of the fastest electron, rather they have given the de Broglie wavelength. Yes, when de Broglie wavelength of the electron is given, we know how to find the kinetic energy of the electron. Okay. So a change in wavelength of the incident light by delta lambda results in the change in delta lambda d in de Broglie's wavelength. Then what is that ratio they are asking, right? So finally, whenever there is a change in lambda, there will be a change in de Broglie wavelength. Simple. See, incident light wavelength is changed. Whenever incident light wavelength is changed, Kmax will change because work function is constant. So Kmax is changed means its de Broglie wavelength also will change because de Broglie wavelength will depend on the Kmax of the electron, right or not? So like that changes what you are going to get that they are asking us. So first let us write this hc by lambda energy of each photon is equal to work function plus Kmax here. And you know de Broglie wavelength, how you are writing in terms of, actually we know that de Broglie wavelength is always equal to h by momentum. De Broglie wavelength of any particle is nothing but h by momentum of the particle. And momentum of the particle you want to write in terms of kinetic energy, momentum is equal to under root of 2km. So from this let us try to write the kinetic energy in terms of de Broglie wavelength first only. So root of 2km h by lambda d. So 2 km h square by lambda d square. So that's what k is equal to h square by 2m lambda d square. So kinetic energy. You have written the kinetic energy of the electron in terms of the de Broglie wavelength. Same thing will substitute here. So hc by lambda is equal to work function plus k max is nothing but h square by 2m lambda d square. Okay. Now clearly it is looking like lambda is depending on lambda d. Whenever, lambda d is depending on lambda. Because when there is a change in lambda, de Broglie wavelength also will change. Okay. Because this is incident, so accordingly you will get k max, accordingly you will get the de Broglie wavelength of that particular electrons. Right. So hc by lambda. Now you differentiate. hc by lambda will be hc into minus 1 by lambda square into d lambda equal to differentiation of work function constant 0. So here you will get h square by 2m and 1 by lambda d square differentiation will be minus 2 by lambda d cube into d of lambda d. Right. Now they are asking, simply minus minus cancels, they are asking change in lambda d, that means d of lambda d by d of lambda. D of lambda d by d of lambda is proportional to only remaining all some constants. So lambda d cube, de Broglie wavelength cube by, so de Broglie wavelength cube by incident wavelength square, lambda d cube by lambda square, that is lambda d cube by lambda. That's proportional to, just we're talking about the proportional to, right? Hope it is clear. So just a combination of photoelectric effect along with the de Broglie wavelength, the best way how they'll try to make it combine all, because in dual nature main thing we are taking photon theory, radiation pressure, de Broglie wavelength and photoelectric effect, right? So in that only they'll try to combine. Right. Next question. Now let us take the questions on the Bohr's hydrogen model. So just look at this question. Look at this question. An electron in an excited state of lithium 2 plus ions has angular momentum of 3h by 2 pi. It is not hydrogen atom, it is hydrogen like ion, Li2 plus, right? And it is having an angular momentum of 3h by 2 pi, something like nh by 2 pi. The de Broglie wavelength of the electron in this state is, okay, they are asking de Broglie wavelength of the electron in this state. So if you have this nucleus and this is, so nh by 2 pi means, actually is it not nh by 2 pi, n is equal to 3, so it is having n is equal to 3. Electron is in the n is equal to 3 state and it will have some velocity, so it will have some momentum. So whenever the electron is having some momentum, it will have some de Broglie wavelength associated with it, correct or not? Okay, that de Broglie wavelength only they are asking us to find. So they're asking us to find de Broglie wavelength means they're asking us to find the momentum of the electron. Momentum is m into v, mass into velocity, right? And since it is Li2 plus, what is the value of Z? Z is 3, lithium ion, Z is 3. Okay, right. So let us start. De Broglie wavelength is equal to h by mv. H by momentum is called as de Broglie wavelength. So h by, but we know very well that mvr, angular momentum, is equal to nh by 2 pi, no? From this mv is what? Nh by 2 pi r. Nh by 2 pi r. H is getting cancelled, so simply you are getting 2 pi r by n, where r is the radius of that, which orbit? Third orbit. But they are giving in terms of the a0 is a Bohr's orbit. Bohr's orbit means first orbit, a0. Okay. So this will be 2 pi by n. What is the radius of the nth orbit? Formula. Radius of the nth orbit. So first of all, radius of the first orbit is equal to, or nth orbit is equal to n square h square epsilon naught square by pi m e square. This is the radius of the nth orbit. Now when you take, this is for hydrogen atom, when you take hydrogen like ion, E square will be replaced with Z into E square. So that is why your radius of the nth orbit will be proportional to, right, one more step, radius of the nth orbit is equal to, so n square is there. If you put n is equal to 1, this becomes the fourth orbit, first orbit. Okay. N square and E square replaced with Z E square. So Z you will put it here, and remaining all h square epsilon naught square by pi m E square. This is all first orbit, radius of the first orbit. So that is why radius of the nth orbit is equal to n square by Z times radius of the first orbit. And radius of the first orbit, according to this, it is a0. Radius of the first orbit is a0 for them. Okay. So here I am putting that. So 2 pi by n, radius of the nth orbit is nothing but n square by Z times radius of the first orbit, which is a0 over. Now n is what? 3. Z is what? 3. So n3 Z3 n square. 3 into 3 9, n square also 3 square 9, gone. So you will get the answer as 2 pi a0, which you are writing as pi, sorry, p into pi a0. So the value of p will be 2, will be the answer. Okay. Okay. So please check it properly. So simple de Broglie wavelength, they are asking h by mv. Okay, not trying to put the value of v, because they are asking in terms of radius. So that is why mv is equal to nh by 2 pi. That way if you put, because mvr is equal to nh by 2 pi, so mv is equal to nh by 2 pi r. Okay. We are back. So we'll go to the next question. Come on, read the next question. Consider a hydrogen atom with its electron in the nth orbital. Electron is there in the nth orbital already. Hydrogen atom only, not hydrogen like ion. Okay. An electromagnetic radiation of wavelength 90 nanometers. Wavelength of the electromagnetic radiation 90 nanometers is used to ionize the atom. And if the kinetic energy of the ejected electron is 10.4 electron volts, then what is the value of n? What is the value of n? So hydrogen atom is there already. Electron is present in the nth orbit, right? So when electron is already present in the nth orbit, for that some electromagnetic radiation is coming and trying to ionize it, Ionizing means what? So you are removing the electron completely to infinity. Even though you are removing to infinity, it still have that infinity, it is still having the energy 10.4 electron volts. The kinetic energy of the ejected electron is 10.4 electron volts. Then what is the value of n? Okay. So just it's all about the two concepts, that is incident photon, how to calculate that energy, and energy of this the electron in the Bohr's hydrogen atom. So which state it is actually, right? See, first in order to solve this, you should know clearly n is equal to first, second, third, fourth. So this is energy is nothing but minus 13.6 electron volts total energy, and this is minus how much? 3.4 electron volts. Okay. N is equal to, and approximately this one will be, because how you will get minus 13.6 by 2 square, n square. So minus 13.6 by 4, if you take minus 3 point. Similarly, minus 13.6 by 3 square, 9. Okay. So 9, so 0.5, 1.5, 10, 5, like this. And something like here minus 0.85 or something like that. Okay, no problem. So roughly you're mainly first and second, you know properly, right? Okay. Next, first we'll try to calculate radiation is having 90 nanometers. In that, how much energy is containing? Okay, so what is the energy of the photon of 90 nanometers wavelength? Means energy will be equal to, already clearly given value by lambda. So 1242 electron volts nanometer by 90 nanometer, right? So this value will come out to be, in electron volts only you will get nanometer, nanometer cancel. So 4, so 9, 8 electron. So this is the energy of each photon you are getting. Okay. So this is the energy of each photon. Now let us say some n value we don't know. Already electron will have some energy. To that you are adding this, right? So 13.8 electron volts you are adding to the electron which is in the some nth orbit. In the nth orbit it will have some energy. To that energy you are adding to this also, plus energy of the electron, the nth orbit, right? If you add, then where it will go? It will go up to, then it will come out of that with what kinetic energy is coming out with a 10.4. So is equal to 10.4 electron volts. It will come out. It will go to infinity. Ionized means coming to infinity. Infinity potential energy is 0, but kinetic energy is there. Okay, potential plus kinetic. Initially, electromagnetic radiation is taken by the electron, which is in the nth orbit, and after taking that, the electron will go to infinity. Potential energy is 0, plus it is having some kinetic energy still 10.4 electron volts. Means what is the energy of this electron? So 10.4 minus 13.8, which will be minus 3.4 electron volts. Clearly minus 3.4 electron volts means which state it is? N is equal to 2. Then only it will have. Okay. So answer is n value, right or not? So that is the meaning difference. Okay, hope you have understood this particular question. Simple, energy of each photon, that is going and falling on the electron which is in the nth orbit. So that is this electron, if you add this energy also, it will go to infinity and it will have some kinetic energy still. Okay. total energy of the electron plus energy of the incident radiation which it is taking, then it will be getting removed from that, means potential energy is 0 plus still kinetic energy it is having. See, the thing is, I'll tell you, suppose instead of 13.8, only let us say 3.4 is only incident on this, then nicely it will go to infinity and stop, that's all. At infinity it won't have any kinetic energy. See, to ionize, just to ionize the electron which is in the n is equal to 2 state, how much energy is required? 3.4. To ionize the electron which is in the ground state, how much energy is required? Just 13.6. Right or not? Now one more thing. Suppose same energy, if it is given to the electron in the ground state, okay, then how, with what kinetic energy it will come out? Correct or not? What kinetic energy it will come out? So 13.8 is equal to 13.8 minus 13.6. Okay, if you do, you will get 0.2. 0.2 electron volts kinetic energy it will come out. So if same energy is given to the electron in the ground state, then it will come out with a kinetic energy of 0.2. Getting my point? So just think energy concept, that's it, right? Already, because energies are negative in those orbits, and you give some positive energy, and if the positive energy is greater than that negative, it will come out with kinetic energy, no doubt about it. Clear? Right. Okay. Next question. Electrons with a de Broglie wavelength of lambda. Electrons with de Broglie wavelength of lambda fall on the target in the X-ray tube. Now we are coming to X-ray tube. So in the X-ray tube, see what is that we will study in the X-rays. In the X-rays, there are two types of X-rays. One is continuous X-rays and other one is characteristic X-rays. So cutoff wavelength, whatever they are asking, it is related to continuous X-rays. Whenever the electrons are coming with high kinetic energies and hitting, if total kinetic energy of the electron is converting into X-rays, then that particular X-rays will have the least wavelength. That particular X-rays will have more energy or the least wavelength. That wavelength we are calling it as cutoff wavelength. Okay, but generally all the total kinetic energy of the electrons will not be converting into X-rays. Some part of the kinetic energy will be converted to X-rays. If all is converted, then that particular X-rays will have a wavelength which is called as cutoff wavelength, and they are asking cutoff wavelength only, right or not? So how do you take? Electrons with de Broglie wavelength of lambda means once electron de Broglie wavelength is given, can't you find the kinetic energy? Yes, why not? So de Broglie wavelength lambda is equal to h by momentum. Momentum is equal to root of 2 km. Here itself, first I will calculate the kinetic energy. So kinetic energy will be equal to h square by lambda square 2m. This is the kinetic energy of the electrons. This is only converting into X-rays. All this energy, if it is utilized for X-rays, X-rays will have energy hc by lambda, because X-rays means electromagnetic radiation, and this lambda only is called as cutoff wavelength. That's all. So 1h is cancelled. So they are asking lambda cutoff. How much? So 2m lambda square c by h. That's it. 2m lambda square c by h. 2m lambda square c by h. Yes. Okay. Hope it is clear. Simple question. Okay. JEE Advanced 2007. Right. Just which is converting to which one. If you make out easily, you can get it. Okay. Move on to the next question. Yes. Yeah. Now we are into nuclear physics. That concept of binding energy of the nucleus, right? The binding energy per nucleon in deuterium and helium nuclei are 1.1 million electron volts and 7.0 million electron volts respectively. When two deuterium nuclei fuse to form a helium nucleus, then energy released in the fusion. Okay. See, the concept of binding energy is very, very tricky, because binding energy concept is such that whenever RHS binding energy, total binding energy of RHS is greater than the total binding energy of LHS, then energy will be released, right? See, two types of nuclear equations are there. One is regarding the masses, one is regarding the binding energies. Suppose if you take in the masses, generally, suppose x plus y comes out to be z. When they give masses, LHS mass is greater than RHS mass means mass is lost. So energy will be released. Energy will be released when LHS mass is greater than RHS mass. But when it comes to the binding energy concept, energy will be released when the RHS binding energy is greater than the LHS binding energy. Okay, so that is a trick in the binding energy, because we know binding energy is nothing but energy released in the formation of the nucleus from its nucleons, or that is the definition of the binding energy, or it can also be defined as energy required to break the nucleus into its constituent nucleons. Okay, right. So let us discuss now. Two deuterium nuclei fuse to form a helium nucleus. So two deuterium nuclei H21 plus H21 forming a helium nucleus He42, correct? And they have given per nuclei binding energy. Binding energy per nucleon in deuterium is 1.1. So how many nucleons are there? Per nucleon it is 1.1. Total how many nucleons are there? 2. So total binding energy of this is what? 2 into 1.1, 2.2. And similarly this one also 2.2 total binding energy. And this one total binding energy will be, per nucleon binding energy is how much? 7. But how many nucleons are there? 4. So total binding energy how much? 28 million electron volts. And here total binding energy of LHS is how much? 4.4 million electron volts. Correct or not? Okay. So this is a 4.4 and this is a 28. LHS, total binding energy of LHS is 4.4, total binding energy of RHS is 28 million electron volts. Definitely RHS binding energy is greater than LHS binding energy, energy will be released. And the difference only energy will be released. So now energy released equal to, so 28 minus 4.4 with 23.6 million electron. 3.6 million electrons here. Alright. So that is a simple concept on the binding energy principle. Okay, same thing will apply for, this is actually something like nuclear fusion reaction. Same thing will apply for nuclear fission reaction also. See, generally nuclear fission reaction, suppose one more question. Suppose X giving rise to Y plus. See, if you look at the binding energy per nucleon curve, okay, so binding energy per nucleon versus that number, okay, mass number, okay, so that time you will be getting something like this, gradually decrease. So somewhere here is the highest, right? So somewhere Z Z values are, so for atomic mass, somewhere for iron and all, somewhere around 50 it is maximum. So this maximum value will be like okay, so something like 8.75. This is in million electron volts. Per nucleon values will be like this only, 8.75, 6 point, like that only. Okay. Now we'll take nuclear fission. One example I am taking. Nuclear fission means heavier is splitting into two lighter, isn't it? So heavier I'll take it here, X. One lighter I'll take Y here, another lighter I'll take Z. Automatically, if you look at this curve, X will have binding energy per nucleon, X value will be less, Y value will be more, Z value is still more, correct or not? So per nucleon binding energy of Y and Z are greater than X. Let us say binding energy per nucleon of X, okay, Z will take this 8.75, no, Z will take 8 million electrons. This I'll take 7 million electrons. This I'll take 6 million electrons. That is okay. And then let us say higher order X, some 200, 120 and 80. Mass numbers. 200 splitting into 120 and 80. Binding, see, compulsory when you can say that energy is released is binding energy per nucleon of Y is greater than X. Each individual RHS, binding energy per nucleon of each individual RHS, if it is greater than binding energy of LHS, like this is greater than this one, and even this is also greater than this one, then compulsory total binding energy of RHS will be compulsory greater than total binding energy of LHS. So let us calculate that. So total is how much? How many nucleons? 120. So total 840. And here total how much? 640. Correct. So total you will get 1440 million electron volts. Let us see here. Per nucleon 6, total how much? 200. So total will be 1200 only. (1440). So which is greater? Definitely RHS is greater than LHS by 1440. So energy released will be 1440 minus 1200 will be equal to 240 million electron volts. Another question, right? So one more observation you are going to find is this is a fission reaction and energy has to be released. Fission reaction and energy has to be released. That is only possible in this side of the graph. Why this side of the graph? When you take this side of the graph only, X is heavier will be this side, lighter will be this side. And two lighter nuclides binding energy per nucleon of two lighter are individually greater than LHS binding energy per nucleon. And energy, that is why energy will be released. See, what I am saying is, nuclear fission should take place. I mean, heavier is splitting into two lighter and also energy should be released means compulsory that reaction has to take place right side. Okay, then only energy will be released. Okay, but same if splitting is taking place here, left side, heavier is splitting into two lighter and left side of this curve, then energy will be absorbed. Okay. And similarly, when you take fusion, two lighter are combining to form a heavier and also energy should be released. That compulsory should happen this side only. Okay, that is the main theme in the when you talk about the curve of binding energy per nucleon. Okay, right. So next we will move on to the next question. To determine the half-life of a radioactive element, okay, half-life of a radioactive element, a student plots a graph of ln of d of nt by dt. Some ln of, okay. Actually, this is nothing but rate of disintegration. Dn by dt is nothing but rate of disintegration, right? For that ln versus t, okay. T of nt by dt is the rate of radioactive decay at time t, we know that. And if the number of radioactive nuclei of this element decreases by a factor p after 4.16 years, what is the value of p they are asking? Okay. So first of all, rate of disintegration, dn by dt. Rate of disintegration, we know that it is lambda n. Yes or no? Okay, lambda n. But they are asking with respect to time. So, but here time is not there. So let us put that lambda n you can write as n naught into e power minus lambda, because you want the relation between this one and time. Okay. So next what I will do is ln of dn by dt is equal to 1, 2, 3, 3 terms are there. So ln of all this can be written as ln of lambda is ln of n naught. Okay. Okay. So and see, ln of all this is ln of ABC is equal to ln A plus ln B plus ln C. So this you can write as ln of e power minus lambda t is nothing but minus ln of e power minus lambda t. What it is? Simply minus lambda t. Got to base e, no? That's why minus lambda t. Okay. Now here clearly they are plotting the graph between this one and t, no? This is some y and this is x. So which is looking like y is equal to, this is x. So minus mx, no? And this all is some constant, so plus constant. That means clearly what we want is a slope. Slope is nothing but lambda. So they have already clearly given this line, and this line slope will be equal to lambda, right? So comparing these two, so you are going to get the slope is nothing but lambda, And why do we want the lambda? When you get the lambda, you can get the half-life period over. Okay, simple. Come on. So how do you get the slope? So slope is not the straight line. Best points what you select here, perfect point. Here also perfect point. And yes, it is a negative slope, this line, because it's a minus m negative slope. But the value will be lambda clearly. So what is value? Come on. So lambda is equal to this by this. This is 1 unit and this is how much? 2. So 1 by 2 lambda. So once you get lambda 1 by 2, just let us try to calculate t half. T half, we know that lambda 2 ln 2 by lambda. Half-life period is nothing but ln 2 by lambda. Okay. So ln 2 is how much? 0.693. But lambda is already 1 by 2. So how much you are getting? So roughly, even if you take 0.7 also into 2, 1.4 means slightly less than 1.4. Okay. Take it as 1.4. In the mind, slightly less than 1.4. That is a T. Right. Now they are asking if the number of radioactive nuclei of this element decreases by factor P after 4.16. Actually, half-life is 1.4, right? Slightly less. Okay, that's understood. So 4.16 means how many times of 1.4? Assume that this is 4.2. So 1.4 into 3 gives you 4.2. So that means how many half-lives? 3 half-lives. And already I told you slightly less than 1.4. If you multiply with 3, you may get less than 4.2. So that's why you are getting 4.16. Okay, so that means how many number of half-lives are there? 3 half-lives are there. So when 3 half-lives are there, initially suppose n naught, after 1 half-life, n naught by 2, after 2 half-lives, n naught by 4, after 3 half-lives, it will be n naught by 8. Right or not? So something like n naught by 2 power n is 3. So 2 power 3, 8. So n naught by 8. So how much it will decrease the number of nucleides? How much factor it is going to decrease means definitely it is decreasing by a factor of 8. Answer is 8. Right. Hope it is clear. Particular question. Right. So that's all for today's discussion. Okay. So hope you have understood the questions properly. All these questions are previously JEE advanced questions, right? And this is one such chapter, whether it is a nuclear physics or whether it is a Bose hydrogen model or whether it is a dual nature of matter. Okay, all these 3 topics compulsory you are going to get the questions. Okay, even the JEE advanced exam also, and these questions you need not have to put much effort. Okay, the simple way, the basic concept, if you are understanding properly, with that basic concept only, you can easily work out these problems, these particular topics. Anyway, especially a Bohr's hydrogen model, already you know in the chemistry also you will be studying, so such an important chapter, right? So dual nature of matter, so you have to focus properly on that, right? Photon theory and all. So these are all constitutes of modern physics. So hope you do well in this chapter properly, and so again, once again, so hoping that you are having a very good preparation for your JEE Advanced and hoping that you write very well in the JEE Advanced exams, right? Thank you very much.